You are currently the only person in this conference.
Okay, so good morning, everyone. So there was a low start because of some connection issue, but finally we are here. So we can start doing some of our exercises. So the idea is to go through last week topics. So we will do exercises. So we do exercises today. And what I like to do is something on conics because we didn't cover them last time. And it will be distances and then circles and spheres. So this is the plan for today. Before starting, do you have any doubt, question, or anything you want to say about, what we did up to now, what we'll do today, and the like? Okay. Okay, seems that all is okay. So we start doing some refresh. So on conics. So we want to say something about conics. So let's say we want to find the type of, and let's write one option, say x squared plus 2y squared plus 4xy equal 1. So let's see what is the type of this conic. So let me see, well, let me know as soon as you have an idea what the type is. So just to remind you, to find the type, we need to decide among three options, right? So it could be elliptic, could be hyperbolic, and could be parabolic. And this is kind of easy, right? Because to decide which type, you have to look to the character of definition of the quadratic form. Elliptic is going to be either positive or definite defined. Hyperbolic will be indefinite, and parabolic will be semi-positive or semi-negative. So there are a few options here. How do we decide? Well, the quickest way is to say, well, I go and produce the matrix A, which we also call sometimes A22, right? So it is 1, 2, 2, 2. That's the associated matrix to the quadratic form. And then what do we do? Well, we have to look for the character of definition. So we play the usual game. Since it is 2 by 2, looking at the determinant, which is 2 minus 4, so it is minus 2, so it is negative. This is telling me all there is to know, because remember, the determinant is the product of the eigenvalues. So this is saying two things. What is the character of definition of this quadratic form? It is indefinite. So it is indefinite. So this means hyperbolic type. So indefinite. This means hyperbolic type. So no more to do at this level, okay? So find the type of a conic is very, very easy, okay? So now let's ask ourselves, let's give a name to the conic, C, and let's ask ourselves, is C degenerate? Synonym of this is also singular, right? So remember, degenerate or singular, for us, it means it splits as the union of lines. So the question we are asking here is basically if the plot of this conic in an appropriate system of reference is something like this, so a nice hyperbola, or something which is of this kind here, a pair of intersecting lines, for example, right? So let's see which one of the two is by deciding if it is degenerate or not. Degenerate will tell you you are in this case. Non-degenerate, it means that by using big coordinates, you're going to be in the other case. Just a question, if Eusebio Alberto want to answer, why did you say elliptic type? Can you explain what reasoning you follow? Of course, it's not correct, but maybe it's going to be useful to see what the problem was if you want to play this kind of game. So why did you say elliptic? In the meanwhile, other people can think about degenerate, singular or not. Okay, so looks like most of you say non-degenerate. Okay. Alberto Eusebio, okay, so there was no special argument. So probably you made it more difficult than it actually is completing the square. I see. Okay, Lantuisi, I must say, why is that, sorry, why is that indefinite? Well, it is indefinite because the product of the eigenvalues, you see, is a negative number. So it means they are of opposite sign. And so it means the quadratic form is indefinite, which means you can take positive or negative values. And so it is why it is hyperbolic. Okay, how do we decide about being degenerate or not? The quickest way is to look at the matrix that we call A33. Okay, the degenerate part is the one we are doing now by Raghi Arch. So we write down the 3x3 matrix, which includes the one we started with. We have to complete it by using the coefficient of x, y, and a known term. So since there is no degree 1x and no degree 1y, we get these. And then we have to look to the known term. So you see, this is -1 equals 0, right? So I will put here a -1. So this is the matrix A33 that you produce. And it is very easy to see that the determinant of this matrix is not 0, right? Just compute it using the third row if you want. You will see is not 0. Being not 0, it means that the conic is not degenerate. So not degenerate. So it means that in some system of reference, in some system of coordinates, sorry, you will have this kind of shape. So to see, oh, sorry, I'm doing the stupid thing, is non-degenerate. You will have this kind of shape, okay? So it is not degenerate. So let's say we make it red, the non-degenerate one, because it is not degenerate. Because degenerate would mean the X shape thing. Okay, so we have a non-degenerate conic here of hyperbolic type. So it will look like the red, okay? Yes, this is the matrix you have to copy and to put here. So was there Manikad? Yes, you are absolutely right. Luckily, it's not going to change the fact that it is not zero. Okay, thank you. Karnauk Sophia says we could put 0, 0 and see if it suits the equation. Now I'm not completely sure what you mean. You substitute 0, 0, and of course you see is not satisfied. It means that our conic does not go through the origin. But you say, if the conic was degenerate, then it would be a pair of lines going through the center since there is no linear part. Yes, so Carnot Sophia is also a nice way of saying that. So if the conic is degenerate, since there is no linear part, the center is the origin. So it must go through the origin. Since it does not go through the origin, is not degenerate. Yep, that's a pretty way of doing this. Yes, thank you. Okay, so let's see another possible kind of exercise we have to do. So find the type of the conic for A in R. And the conic we want to study depends on this real parameter is the following. So it is x squared plus 2y squared plus 2axy, say equal 1. So we want to find the type of the conic, but it will depend on the real parameter A. So the answer is not going to be it is hyperbolic, it is elliptic, it is parabolic. It's going to be it is hyperbolic for these values of A, elliptic for these values, and parabolic for these other values, okay? So let's find the type of the conic for A real number, okay? So let's see how you do this and let me know what you get. Usually in the multiple choices, you see this question in the shape of are there values of A making it of elliptic type, are values of A making it of parabolic type, and so on. So if you manage to find a type, depending on A, you are on the safe side. Okay, I'll give you, say, 1 more minute to let me know if you have any idea that you can easily write, or we will do this together. That's good both ways. Okay, so let's go. Okay, so Sofia Carnau got a nice description and Vespur Alireza too. So let's try together. So I look at the matrix A22, 1, A, number 2, and then I want to study the character of definition of this one, right? So I'm going to look at the character of definition, which means the sign of the eigenvalues. And again, since it is 2 by 2, it's going to be very easy, because using determinant and trace, we are going to be safe. So the determinant is going to be 2 minus a squared, and the trace is going to be equal 3. So being the trace equal 3, for example, it means it's not going to be negative definite, right? But it could be positive definite or indefinite. So everything which is important here will depend on the sign of the determinant. So let's see what we get. So the determinant of A22 is larger than 0 if and only if. What happens? Well, you know, we are looking at a degree 2 equation of this kind. So it's going to be positive when we are in the interval of the roots. So if and only if A belongs to the open interval minus square root of 2, square root of 2, right? It's going to be negative exactly in those 2 points. A belongs to minus square root of 2 and square root of 2. And it's going to be negative when A belongs to the open interval. So belongs to minus infinity minus square root of 2 union square root of 2 plus infinity. Okay, so this is the description, so which looks like probably yes. So Sofia Carnauck, you probably overlooked the fact that there are 2 roots. Yes, yeah. You forgot the minus sign. Okay, so these are the 3 situations. Let me finish this right for a second. So what happens in this situation? So the equals 0, 1 is the parabolic type. Yeah. While the greater than 0 part, it means eigenvalues of the same sign. It means elliptic. While the negative part, which we see here, it means eigenvalues of opposite signs, so it means hyperbolic. Okay, so these are the 3 situations we have. Well, Paolo Lovero asked about the role of the trace. Well, the role of the trace is what you need if you want to find the character of definition. So for example, in this situation, you only know that the eigenvalues have the same sign, right? So you're saying that lambda 1 times lambda 2 have the same sign. This one tells you that lambda 1 plus lambda 2 is equal 3. So if you want to study the character of definition, you also need the trace. But to study the type of the conic, it's just enough to know about the sign of the eigenvalues respect to each other, same sign or opposite sign. Okay? Good. And now these are the 3 descriptions. And then Sinalbi says, can this conic be degenerate? Well, let's ask for that. So is C of A degenerate? For any A in R? What do you think? Is it degenerate for any value of A in R? How do we answer? Well, it is the usual way. So the fail-proof way is to look at matrix A33, which is made by, if you think, in this case, it's just putting some zeros there, A22 here, and then it will be number 1 in the corner, right? Well, probably -1 in the corner. And so, since this is a block matrix, the determinant of A33 is equal to minus the determinant of A22, right? And so you see, it's 0 if and only if it is 0. So Grasso Beatrice says, yes, it is degenerate exactly when it is of parabolic type. So there are values of A for which we obtain degenerate conics. Yes, there are. And it is only happening when they are of parabolic type. So parabolic degenerate, it means parallel lines, right? Or two coincident lines, okay? So it is degenerate if and only if A is equal to minus square root of 2 or square root of 2. So we can put it here. So it happens if and only if. So let's put it here. Yep, C of A degenerate if and only if A belongs to minus square root of 2 and square root of 2. So it's going to be degenerate and parabolic type. So we said it will look like two parallel lines, maybe coincident, maybe distinct. Okay, if you want to know, you have to go and check more carefully what you get. But in this situation, they will not be coincident, again, because of the center situation we have. Okay, any question, doubt, or remark about this one? So scroll up. I hope it is enough. Okay, so if all is good, let's say that now we move to a slightly different set of questions. So here it is. We are given, say, some geometrical objects, say four, well, actually 5 of them. So the first two are points. One is the origin. One is point Q, 1, 2, 3. One is a plane, pi. One is a line, R. And one is a line, S. Okay, so what we want to do is to compute. So compute the distances. So you want to compute the distance between X and Y, where X and Y are chosen to be, in turn, one of the objects you have here, okay? So my suggestion is that as a warming up, we start with, well, the easiest one. So the distance between P and Q, this is very simple, right? So we are just given 2 points. You want to measure the distance of this segment, so it is the magnitude of P minus Q, okay? So it is the magnitude of the vector you get as a difference of the coordinates. Very simple in this situation, because one is just the origin, so it is the square root of the dot product of 1 to 3 by itself. And so it is just square root of 1 square plus 2 square plus 3 square. Okay, nothing to do for this, right? Then the next step is to compute, for example, the distance between P and pi. So let's see what is the distance between point P and plane pi. So what do you get here? And remember, to find the distance between a point and a plane, you have two ways. Either you look for the intersection orthogonal projection, or you use the formula, okay? And in this case, it's very simple to see it is 0. Why? Because point P belongs to plane pi. Exactly. So now what happens if I use point Q instead? So what is the distance between point Q and plane pi? What do we get here? So we have also the plane, and the point Q is 1, 2, 3. So what do we get as a distance here? Well, you can use either the formula or project and take the distance between the projection, orthogonal projection, and the original point. So let's see what you get. Okay, so we have a number, and what is the process? The process is take the absolute value of the evaluation of the point. So remember, just Q is 1, 2, 3. Plane pi as equation x plus y plus z equals 0. So you will get 1 plus 2 plus 3. And then we take the absolute value, and then we have to divide by the magnitude of the normal vector. So 1 square plus 1 square plus 1 square. So we get 6 over square root of 3, which you can write actually as square root of 3 times 2. That's fine. Okay, so this is kind of straightforward. Okay, now let's see, for example, how we can compute the distance between, for example, say the plane pi and say the line r. So to compute the distance between a plane and a line. So what do we get here? Federico Morro says 0. Why is that the case? Because the plane pi actually contains line r. So you get 0 because pi contains r. Why is that the case? Well, because you see that one of the equation of r is exactly the equation of the line. However, how do you compute the distance between a plane and any line? So for example, suppose you want to compute the distance between pi and s. Well, what you have to do is see if the two intersect, or if they don't intersect, well, they must be parallel. And if they are parallel, it is just enough to pick a random point on the line and get the answer. Okay, so pi and r is 0. We can see it easily. S and pi, sorry, we have to decide whether the line and the plane are parallel or not. If they are not parallel, then it is 0 because they will intersect. If it is not, the case, so if they are parallel, then it is just enough to pick any point on the line, and then the distance between the plane and the line will be equal to the distance between the point and the plane. So this is case 1, this is case 2. So let me know if we are in case 1 or in case 2 for line S. And then once we know that, we will go and compute. Please scroll up. Yep. Okay, so someone says they are intersecting in the origin. So what is the distance? It is 0. So what you are saying is that the line S, which is here, and plane pi intersecting the origin, and that's true. So the distance is going to be 0. So we are in this case here, 0, 0, 0. So the distance is 0 because pi intersect S is not the empty set. And Alireza, there is no intersection formula. There is no formula we use for lines yet. No, this is the first case. Yeah. Okay. So now we can do the distance, for example, of one point. So let's say we take the distance between point Q and line R. So what do you get here? Just as a quick reminder, so we have a line, we have a point. How do we compute the distance? Well, the ideal would be to compute the orthogonal projection and then to compute that distance. And this can be done very easily by using a plane alpha, which is orthogonal to R, containing the point Q, and then H will be the intersection of alpha and R, okay? So this is my suggestion to compute the distance between Q and R. Of course, if Q belongs to line R, well, then the distance is going to be 0. So let me know what you get in this situation. So let me know when you have some news about this case here. Okay, give you 1 more minute so you can finish your computations. If you manage to have point H, it would be already good enough. Yep. Okay, so we have one possible answer by Riaki Pascal. We can also ask Riaki Pascal to tell us what is H, what are the coordinates of point H. Okay, so 0, minus 1 over 2, 1 over 2. So let's see if Riaki Pascal got the right idea. Okay, so it is easy to check if H is the correct one because, so let me write with a question mark. Dot is not that I don't trust you, but we need to check. So first, is H a point of line R? What do you think? Is it a point of the line or not? Well, we go and substitute, right? So the sum of y and z is 0. So this equation is right. Since this is 0 and x is 0, also this equation is correct. So we say yes. Then what do we have to check? We have to check the vector q minus h is orthogonal to the direction vector of line R. So we need to compute the direction vector of the line. This you can do in many different ways. One way is to write the line in parametric form or use the cross product of the direction vector of the two planes which give you the line. So what you see, the second equation tells me that y and z are opposite. So if y is minus t, then z is t, and so x is 0. So the direction vector we see here is something like 0, minus 1, 1. Right? So x is equal 0, y plus z is 0, so t minus t. And so what we want to check here, so this is going to be true if and only if the dot product is 0. So let's write down the vector in our slang notation. Q is 1, 2, 3. So I have 1, 2, minus 1 over 2 plus 1 over 2, and 3 minus 1 over 2. And then we do dot product with 0, minus 1, 1. And so what do we get here is 2 plus 1 over 2, well, with a minus, plus 3 minus 1 over 2. So what we get is, well, 3 minus 2 minus 1 over 2 minus 1 over 2. And so we get actually 0. So they are orthogonal again. So it is correct. So H is actually the orthogonal projection. So once we have H, what we know is that the distance between the line and the point is going to be the distance between Q and H. And so this is the magnitude of Q minus H, which we can easily compute now because Q minus H is standing here for us to be computed. Okay, so this is showing that Riaki Pascal, Carnauck, Sophia, they probably got the right answer. Just a quick thing before looking in the chat. How do you compute H? Well, you take the parametric equation of the line, for example, this one, and you substitute into the equation of the plane. And then you solve for t, and then you compute point H. Vespur Alireza says, how can I find, I think your question is, if a plane contains a line? Okay, well, so let's make a quick note. So a plane alpha contains a line L if and only if the intersection is the line itself. Okay, so for example, what is necessary is that the direction vector of the line and the normal vector of the plane are orthogonal. So, for example, the intersection means that an alpha is orthogonal to VL. That's not enough because that would mean just parallel, but then they have an intersection point. So it is what you do. You just solve the system by intersecting. You have to find infinite to the one solutions, or if you prefer, you look for direction vector, normal vector. If they are not orthogonal, the line is not in the plane. If they are orthogonal, then the line is inside the plane. Okay. Another quick note I want to make since you asked is the following. So you see, a line L is given as the intersection of two planes, say P, well, let's do like this. So I have two planes, alpha and beta, and here I have equation 1, and here I have equation 2, okay? So what happens is that if you take any number times equation 1 plus any number times equation 2, this is going to be, it is a plane containing L. And actually, all planes containing L come in that way. Why is that the case? Because you see, here you have plane alpha, here you have plane beta, and this means that each single point on this line satisfied both equations. So satisfies equation 1 and equation 2. So you see, any point on the red line will satisfy this equation here that you are going to write. So for example, if we look at our line R, so in our example, so for example, have a look at line R, which is x plus y plus z equals 0 and y plus z equals 0. Then if you take a times x plus y plus z plus b times y plus z equals 0, and you make a and b vary in R, you find all possible planes containing the line R. So all possible planes through line R. Okay, so this is a way of finding all possible planes containing a line by taking linear combination of the two planes. Oh, can you write a plane containing this line? Well, there are infinitely many planes containing this line. So you just give values to A and B as you wish. So for A equals 0, B equal 1, you get this plane. B equals 0, A equal 1, you get this plane. A equal 1, B equal 1, you get the plane X plus 2Y plus 2Z equals 0. It's different from these two, but it is another plane containing it. It's just substituting values of A and B in R as you wish. Okay? So I don't write it down because it's already written. So let me know if this is clear. So in the meanwhile, let's see a new kind of exercise. So say we want to compute center and radius of circles. In the plane, we don't spend much time, right? It's just completing the squares. So we want to do this in 3D because it's where it is more probably challenging. So x squared plus y squared plus z squared equal 1, and say x plus y equals 0. So tell me, what is the center and what is the radius? Okay, so Cornau Sophia suggested, well, it is the origin and the radius is 1. So I think there is no problem to see that the center of the sphere is the origin and the radius of the sphere is 1, okay? Because it is in canonical form, say. And then we just note that the plane pi, so pi contains the center of the sphere. This means C has the same radius and center. This is always going to be true. So if we want to make a rough sketch, so if you have your orange and you cut it with a plane going through the origin, sorry, the center of the orange, then it will have the same radius and the same center of the orange itself. So it's like on the surface of Earth, if you look for meridians, okay? So it will be the same radius and the same center. That's very easy and good to remember. Now, I suggest you consider a new circle. So I write it here in a different color, say green. So let's look at C prime, which is like this: x squared plus y squared plus z squared plus x plus y equal 1, and then x plus y equals 0. Now you see something is changing because the sphere above is different. So what do you think now about C prime and R prime, radius and center of this circle? What do you think? I wait, say 2-3 minutes for you to come up with some nice answer. Okay, so Alireza produced an answer. I just wait for a couple of minutes to see what do you think of that answer. So in the meanwhile, I'll do this cut and paste. Put it here so we can look at them at the same time, right? And I'd like you to think about a system of equations for a while. So the blue one is the system of equation defining C, and the green one is the system of equation defining C prime. Do you agree that the C's system of equations are equivalent? Because if you call this one equation 1 and this one equation 2, then the grid system is just the same equation 2 and equation 1 plus equation 2, right? So the system are equivalent. And so they have the same solution set. Okay, yes, Karnauk Sophia. Yeah, they have the same solution set. Do you agree? So they are equivalent system because you use just a linear operation. So thus, the systems, so the two systems, they are not linear, but they are equivalent, have the same solution sets. This means that C is equal to C prime. So the two circles are equal. Being equal, they must have the same center and the same radius, right? So hence, C prime is equal C, equal the origin, and R prime is equal R, equal 1, because they are equivalent, okay? The systems are equivalent, the solution sets are the same, so you get the same circle. Graphically, this is not so difficult to see, because you can proceed in this way. So you have the same green plane, which is pi. Then you have a circle here, which is, say, circle C, which you obtain by intersecting with, say, the sphere of the blue system, which is something like this, say. Okay? But then you can also obtain the same circle by intersecting with another sphere, which is the sphere of the green system. Okay? So what is the situation? The situation is that maybe the same circle can be defined by different systems, by different sphere intersecting, for example, the same plane. So the center and the radius of the circle will not change because it is the same circle but written in a different way. Okay? Sophia says, if we solve the system, do we really get the equation of a circle? Well, Sophia, that's not clear to me what you mean, because there is no one equation of a circle in 3D. A circle in 3D is defined by one parametric equation, which we did not consider yet, but it is defined by two equations. And there are very infinitely many spheres and planes intersecting in that circle. The plane is uniquely determined, but the sphere is not. Okay? The circle determines a plane, but not the sphere. There are infinitely many spheres. And there is no one equation of the circle, one parametric, but you need two Cartesian to get it. Okay, so my message is, you see, sometimes if you play with the equation, you can write the same circle in a simpler way. If you stay with the green situation, well, nothing will go wrong. So now we make the computation here. But what I want to say is that you can make your life much, much simpler if you think of what we are doing here in defining objects as solution sets of system of equations, okay? So let's say we make it as a different exercise in which you want to compute the center and the radius. So what is the approach? The approach is to complete the squares so that we can find the center and the radius of the sphere easily. So here we have something like x plus 1 over 2, well, sorry, x plus 1 over 2 square, and I have to take away minus 1 over 4, right? And this will produce x squared and x. Then I have y plus 1 over 2 square minus 1 over 4, and this will produce y squared and y. Then I will have z squared, and then it is equal 1. So what we get as center of the sphere is minus 1 over 2, minus 1 over 2, and 0. And what we get as radius, say, square of the sphere is 1 plus 1 over 4 plus 1 over 4. So we get, what is that? 1 over 4 plus 1 over 4 is 1 over 2, 3 over 2, okay? So this is the center of the sphere, S, and this is the radius of the sphere, S. Now, for example, how do you produce C prime? Well, these we remember. I look at the sphere, I cut it with the plane, pi, x plus y equals 0. And what I need to do to find C prime is the orthogonal projection of C on that plane and intersecting. So we need to find the line L, which goes through the center of the sphere, 1 over 2, 1 over 2, 0, and it has the direction vector, which is the normal vector of the plane, okay? And then you have to intersect with the plane. So L intersect pi, I find by solving 1 over 2 plus t plus 1 over 2 plus t equal 0, which happens exactly when t is equal minus 1 over 2. And this gives me as C prime the point I get by substituting minus 1 over 2 in the parametric equation of the line. So I get 0, 0, 0. Okay, so this is how you get the center of the circle defined by the equation. C prime is 0, 0, 0. Now, how do you get the radius of the circle? Well, we need to remember what we learned last time. So that the radius of the circle is related to the radius of the sphere by the distance. So what we get is that the radius of the circle square is equal to the radius of the sphere square minus the distance of the plane by the center of the sphere square. So what we get here is 3 over 2 minus, and then you need the distance between pi and the center of the sphere. So I have to divide by square root of 2, and then I will square everything, and then I have to substitute the coordinate of the plane, of the center in the one of the plane. So I get minus 1 over 2, minus 1 over 2. So you make this computation, and you get exactly the result we were looking for, okay? So this is just applying Pythagoras theorem. We take r squared minus the distance, square, and then we get the answer. So the message here is look for hidden meaning, hidden geometrical properties, which are clear from the algebraic structure. The algebraic structure sometimes will reveal these hidden geometrical properties for you, making life much, much easier. Okay? Okay, similarly, we can play any question about this before we go further? So is this up good enough? So now we will do again one of these computations, and then we change topic a little bit. Okay, so one more of this computation. Again, compute the radius and the center. And the center of the following circle. Here it is. It is x squared plus y squared plus x plus y minus 1 equals 0. And it is x squared plus y squared minus x minus y minus 1 equal 0. Okay, so we want to find the center and the radius of these precise circle. So let's see what you get. Okay, so some of you realize that the answer is the same. However, how do you proceed to intersect two spheres? Well, we said that C is going to be defined using the radical plane, right? So you take the same situation, equation 1, equation 2, and then you take the difference because these will make the quadratic part to go away. So what you get here is minus 2x minus 2y minus 2 equal 0, right? No, not right. Is equals 0, period. So what I do is x squared minus x squared, y squared minus y squared, minus x, minus 2x, minus y, minus 1, minus 1. So basically what you see is that the plane you see here is actually x plus y equals 0. So you are intersecting the two spheres here, and you will get the same answer as intersecting this sphere and this plane, and you will get the same answer as intersecting this plane and this sphere just by, and sorry, I was a little bit too quick here, there is a z square missing, otherwise it's not a sphere situation, sorry. Now I understand why some of you were confused. And so we get the same situation we got before, radius 1, center 0, 0, 0. Okay, so my bad, there was a z square missing at the beginning. So this is why Carnot Sophia said about the intersection of the two cylinders. It was my bad. In writing, I copy wrongly from my notes and I made it into something not comprehensible. So here is the version I want to show you. So I have a sphere and a sphere. So it is a circle in 3D. I want to find center and radius. Suggestion is play with the equation so that the radical plane will show up. And then you can simplify again using the radical plane, the first equation. So you will get to a situation that we know well. If you're missing one variable, that's something interesting. It's something that can be studied, but it is not something we are going to do. Not now, okay? So thank you. Now we change topic a little bit and say, as an example, we want to compute a circle C, tangent in P to the line L, in the case in which L is the line x plus y equals 0, and the point P is the origin. So graphically, what is the situation? Well, we are in the plane x, y. We take a line, the bisectrix. So this is line L. We look at point P, which is the origin. We want to find a circle tangent to the line passing through the origin. Of course, there are many circles like that, right? It's not a question of does the circle exist? There will be many circles, okay? And actually, there will be infinitely many, very large and very small, okay? But we want to find one. So let's see how you do that while I go and get the charger before it's too late. Okay. You're right, but we don't change the line, right? We just change the equation here. Thank you. Well, it's June, right? So we have to pay extra attention to everything we do. Okay, so Karnaug-Sophia produced a suggestion, and it says, well, I can look at all these circles. So there is a parameter t, and she says they are all going to be tangent to the given line. Well, one thing is, how do we check if Sophia Karnaug is correct? So she's proposing circles depending on a parameter t. Let me copy. Hopefully I can do this correctly. Minus 2y plus t squared equals 0. Then I want to intersect with the line L. So basically what we want to do is solve the system having x minus y equals 0, which is the line L, and the equation of the plane, circle. So what can you do? Well, you see, what you can do if you want to compute this intersection is to say, well, the first equation is telling me that x is equal y. So I can substitute the first equation in the second. But I have a question. Did you, Sophia Karnaug, use the line x minus y equals 0 or x plus y equals 0? I'm afraid you use the x minus y, x plus y equals 0. So the computation given by Sophia Karnaug is for the line x plus y equals 0. So her answer in our situation would be like this. So a plus in this place, okay? So you substitute and you get x squared plus 2x minus 2x plus t squared equals 0. So these two you see cancel out and you get something like x squared plus t squared equals 0. So probably we have to put a minus here to make things correct. So small computational mistake. But then you see, what do you get at this point? So you get a condition, x squared minus t squared equals 0. So you get two distinct solutions, right? So what do we want is not exactly this, but this is not Sophia Karnaug's suggestion, is my suggestion. So my suggestion is saying that, well, the circle you produce will intersect line L in two distinct points unless t is equal to 0. Okay, but this is because I change the line. Okay, so this solution is not the one we want, but that's because there was a change of the line during the computational process, but we can adjust it very quickly. So what is the idea? The idea is that all these circles have something in common, which is the fact that the center is on a line orthogonal to L and going through P. Okay, so C as center on the line x plus y equals 0. So the circle you're looking at are of the shape x minus t square, x plus t square, right? And then what do you have to put here is the distance between the center minus t, t minus t, e minus t, because this is the point t minus t, and the point in which you want the tangent. So you want the distance between the point t minus t, which is the center of our circle, and the point P, which is the origin. And this is just square root of t squared plus t squared. So it is twice absolute value of t, if we want to do like this. And in this way, we produce all these kind of circles, right? And in this way, we produce all circles having center on the line x plus y equals 0 and having distance from the origin equal to the radius. Oh, sorry, there is a square here. So this is my bad again. So 2t squared. So repeat, the center is t minus t, so here it is, and the radius is the distance between t minus t and the origin square, so you get this expression here, okay? Yeah, Moro Federico, yeah, you are correct. I realized that just a second before, but this is what you can do. And so you can find all these equations, okay? And now, if you take this equation and you substitute x equal t, sorry, x equal, and of course, this is y, right? Because we want to have center t minus t, x and y. Okay, so this is the situation we want. This is how you can construct all these circles, and you work out the computation and you will get something very similar to what Sofia Carnau got before. So these circles CT have center t minus t, and they have radius equal to the distance between the center and the origin. So they are all tangent to line L in the origin, okay? Okay, so what I want to make you note here is the following thing. So this equation, we can rewrite a little bit more nicely as x squared minus 2xt plus t squared plus y squared plus 2yt plus t squared equal to t squared, which means it is x squared plus y squared minus 2xt, well, say minus 2tx plus 2ty equals 0. So this is the circle we are looking at, right? Now, if you intersect this circle with line L, you are solving the system having x minus y equals 0 and equation of the circle of this kind. Here it is. So what you can do is say, well, system of equation x minus y equals 0. I use the fact that x is equal y, so I get 2x squared equals 0. And so I get the solution x squared equals 0 and x minus y equals 0, which is what we can call a double point. So just one point of intersection with the line we are looking at, right? So you see, this is telling me that our solution is correct for all value of t, because when I intersect, I just intersect in 0, 0, which counts twice because of the x squared. Okay? Is this clear? Okay. So we are already over our time. So we have to wrap it up. But here is my note. You can take the x squared plus y squared equals 0 circle, which is a degenerate circle, which is just the origin. Then you take the line x minus y equals 0. This system is defining just this double point on the line on x minus y equals 0. So if you produce an equivalent system, all will be fine. So I can produce an equivalent system by just playing with equation, as some of you suggested. But now you see, this was a degenerate circle, just one point, while this is a regular circle. So by changing the parameter t, you get everything you need also here, and you produce all circles. So the idea is that you can use a degenerate circle passing through the point P, the line you want to be the tangent line, and just playing algebraically, you get all possible circles. This is something we will see again next week. Okay, I think, yes, our time is over. So you should go to your next lecture and see you next time, right?